So in terms of interpreting this model then, I want to try and give you a feel for what's really going on here. This is important. It's also not just a maths thing. So some information from the context of the wider problem is important here and should feed into your analysis. So what we're trying to do here is model the probability of success in terms of the load, and it's natural to think that the component is more likely to fail as the applied load increases. So equivalently, you might expect the success probability is likely to decrease as the applied load increases, and so it's natural to expect that you would get the coefficient of beta 2 in this regression equation to be negative. Okay, so there's a couple of conceptual leaps that are important here. Firstly, we're trying to model a probability, and the component is more likely to fail if the load increases, which is the same thing as saying that the success probability is likely to decrease as the load increases. And as I said before, it's worthwhile thinking about these things in terms of success and failure, and that will help you, if you do that, to sort of match with how the R commands for these models are set. So the linear probability model then, so the fitted value of the regression model is to be interpreted as a probability that a component succeeds given the load that is applied. Now, since this is a probability, you must have that all sensible probabilities lie between 0 and 1. So if the probability here, equation 2 on this slide, then you must have that this equation is between 0 and 1 because probability. Now this seems absolutely straightforward and is just a repetition of high school maths, but there's no guarantee actually that this equation holds unless additional constraints are imposed. And these regression models that we're considering, these probability regression models, actually impose these additional constraints to guarantee that the probabilities that you obtain are sensible estimates. Now if you just have a straightforward regression model, this linear probability model, and you don't make any adjustments in terms of how you calculate probabilities, you can reasonably anticipate that for either very low values of the load or for very high values of the load, you get non-sensible probabilities. So if the load is very low, you might have a success probability that's estimated to be bigger than 1, and if the load is very high, you might have a success probability that is estimated to be less than 0. Okay, from high school maths, these make bonkers probability estimates. So I wanted to sort of go through this a bit more than this linear probability model. So you're interpreting the fitted value of this regression model to be the probability that a component succeeds given the load that's applied, to make sure that you impose a constraint so that any estimated probabilities do indeed lie between 0 and 1. Now that is the main thing that I think here is important, that any sensible estimates of probability should lie between 0 and 1. Now the textbook by Gujarati and Porter makes a big deal of these two things here, that there is a contravention of the standard regression modelling assumptions. Firstly, that the disturbances are non-normal. Secondly, that you've got heteroscedasticity. Now, whilst these are true, I think it's a little bit uninteresting to say this, as the big deal surely is that any estimated probabilities that you get must lie between 0 and 1. Okay, but sometimes econometric textbooks make a big deal of these things here, in that in this case you can show that the disturbances are non-normal and that the disturbances are heteroscedastic. So in both cases there is a violation of the classical linear regression modelling assumptions, and it's not usual that you can illustrate this so cleanly mathematically. Okay, it's not necessarily interesting in itself though. So as I was trying to say there, sometimes these econometric books try and emphasize that this is one of the examples where you can emphasize that the disturbances in this regression model are normally distributed. So since probabilities are greater than 0, you have this first equation up here, so ui must be bigger than minus beta1 minus the beta2 load value. Since probabilities are less than equal to 1, you must have the value is 1 minus b to 1 load. The conclusion the terms must be within this bound here shows that the UI can only take certain bounded values, and so necessarily then it can't be normally distributed, because random variables that are normally distributed can take any value at all, positive or negative. It's just that you might get low probabilities of extreme events, but here there is probability 0, the UI values. The UI you bounded must be that the UI cannot be normally distributed. So this is a little bit of background maths. It's not necessarily so interesting. It's just I wanted to emphasize here that this is one of the examples where you can demonstrate the regression residuals cannot be normally distributed. So this should say here the heteroscedasticity of the UI. So since the y variable in the regression model is a probability, then you must have that is greater than or equal to 0, which gives you the first bound for UI, and then the probability must be less than or equal to 1, so this gives you the second bound for UI. So the conclusion again is that the UI can only take certain bounded values. The bounds depend on the value of the load. The distribution of the UI then necessarily depends on the load, and hence the variance of the UI must also depend on the load. So the variance of the UI depends on the load, and so this means then that the UI has a different variance depending on what the value of the load is, so the UI is not homoscedastic. In contrast then, the UI is heteroscedastic, and I apologise that this may not be much of a spectator sport. The reason this is important is that it's sometimes an example that's discussed in these econometric books to illustrate a sort of nice, easy to write down example where the UI cannot be homoscedastic. Okay, the bigger deal though, as I tried to say before, is that if you use this linear probability model, some of the probabilities that you estimate may not lie between 0 and 1. So in summary then, the linear probability model seems to be nice and easy, and it's intuitively appealing. It does combine a linear regression model with an estimates of probability. So there's a linear bit and a probability bit, hence named linear probability model. It's not so useful in its own right. Really, it's just teaching material, and really the best way it can be used is to illustrate how to estimate probability sensibly using a logit model or a probit model. For whatever reason, a model has been misguidedly popularized by classic econometric texts like Gujarati and Porter. I think with this linear probability model, you're likely to get relatively sensible estimates of probabilities in the middle of the sample, but as we'll show later in the lecture, extreme X values are liable to lead to probability estimates that are either going to be less than 0 or greater than 1. Okay, and going back to high school maths, any probability that should make sense must lie between 0 and 1. Whilst that's quite a simple observation, it's not necessarily simple in terms of the underlying mathematics, and we need harder regression models here, the logit and the probit model, to ensure that any probability estimates that you get sensibly lie between 0 and 1. Okay, so this is perhaps more involved than you might imagine would be the case. So I wanted to sort of talk about this problem in mathematical terms, okay, with some equations, but there's a pictorial illustration of this in the next slide. So for linear regression, what you have is the y variable is equal to some combination of the x variables, and then for probability regression, what you have is some function of the probability of y is then equal to the regression bit instead. The idea is that regression bit b to 0 plus b to 1x1 plus all the way to b. That can take either positive or negative values, depending on what the values of x and beta are. But whilst that's true, genuine probabilities must lie between 0 and 1. Okay, we haven't lost any common sense or mathematical ability since high school, and the main thing here is that sensible probabilities must lie between 0 and 1. Now this function in equation 5 here is known as a link function. Now these are deliberately named, although this is a technical statistical term, but what it is doing is just literally linking the regression part of the model to the probability calculation. Now this might sound really difficult, but it's actually quite easy to illustrate this with the figure on the next slide. So what happens is if you have a straight line, you need to sort of squash this in somehow so that any probability estimates you obtain lie between 0 and 1. And that is all this link function in equation 5 is doing. So behind the maths then, what is really going on is this picture here. So if you look at the picture on this slide, what you've got is a picture of a simple straight line linear regression model. And what you should see that if the x variable is sufficiently large, then any estimated probabilities beyond that point will be greater than 1. So nonsensical. Equivalently, if the x value is sufficiently small, then any estimated probabilities beyond a certain point will be less than 0. Again, nonsensical. And what you need to do in some sense is take this regression line and squash it so it lies between these two tram lines here at 0 and 1. And then if you come up with a suitable way of squashing this regression line, necessarily then any probabilities that you estimate will lie between 0 and 1 and will be as we would imagine from high school maths. Okay, and all that is happening is that the f function, the link function on the previous slide, is just this way mathematically of squashing this regression line down so that any probabilities that you estimate necessarily have to lie between 0 and 1. Okay, so there is some technical mathematics in the background and a few equations, but all that's happening here is you're taking this regression line and you're squashing it down so that any estimated probabilities have to lie between 0 and 1. So the point then is you want to keep the regression bit, but still make sure that you can estimate sensible probabilities. So the first equation there is a regression bit, so you've got beta 0 x1 plus bxp. So this can take any values at all, positive or negative, and you need a link function f to squash the equation down exactly as shown on the previous slide so that you get sensible estimates of probability that lie between 0 and 1. So in this case what you would then have of the probability is equal to this regression bit, and that's all this equation here says. So that some function of the probability is equal to beta 0 plus beta 1 x1 plus all the way up to beta p. Do this in the right way, much of the standard interpretation remains the same. So you still have things like t-statistics, etc., and still do the same basic suite of hypothesis tests, but these things now refer to probabilities. So that if beta I is greater than 0, then as xi increases, the probability increases. And similarly, if beta I is less than 0, then as xi increases, the probability decreases. So that any change that occurs happens to the probability of y, not to the y variable itself necessarily. So logistic regression then, so this is essentially the first real probability regression model that we will cover in this lecture, and the whole aim of the game is to regress or explain probabilities. What the regression model does is provide a way of squashing probabilities that they lie between 0 and 1, exactly as the picture demonstrates a couple of slides ago. So suppose you have a regression model like this, so the log of a 1 minus probability equals the regression bit. You can calculate in this case the probability as follows. So the first step, what you would do is take the exponential of both sides, log our inverse function, so just where you started with there. Basic manipulations, just algebra from acutely where it's not a spectator sport. You can solve this to see that the probability that's estimated is equal to the exponential of the regression term over 1 plus the exponential of the regression term. This final equation gives you a way of short-circuiting some of the logistic regression calculations, and what you can see here is that necessarily any probabilities that you calculate like this must lie between 0 and 1. Okay, so mission accomplished. According to this model, any probabilities will lie between 0 and 1.